everyone, I'm Justine and I'm part of the postgraduate course Introduction to Earth Observation Sciences, and I'll be presenting my project brief on coastal resilience, leveraging remote sensing for integrated coastal management in the Philippines.
Just to provide a quick background of the study, the Philippines, being an archipelagic country, faces significant challenges related to coastal resilience, including high population density in coastal regions, frequent natural disasters such as typhoons, and vulnerability to sea level rise. Additionally, the high cost of data collection and analysis, coupled with limited budget allocations for monitoring, exacerbates these challenges.
Thus, there is a pressing need for a systematic approach to monitor these coastal areas. This project, therefore, aims to provide a framework for planning units in the Philippines to follow a remote sensing process for a more holistic approach to monitoring the coast, managing anthropogenic forces, and preparing for environmental hazards. Remote sensing involves acquiring information about the Earth's surface without direct physical contact using sensors mounted on satellites, aircraft, or drones. Coastal land cover, land use, and environmental hazards are critical to monitor, requiring specific sensor capabilities. For example, mangrove forests need near-infrared and shortwave infrared bands for differentiation, with high spectral resolution and frequent temporal monitoring. Coral reefs benefit from blue and green bands to penetrate shallow waters, demanding very high spatial resolution. Coastal erosion requires visible bands and moderate spatial resolution with seasonal monitoring to track changes. So the selection of remote sensing data is based on these specific requirements of monitoring coastal land cover, land use, and environmental hazards. Particularly, Landsat-9 OLI and Sentinel-2 AMSI were chosen for their spectral capabilities and spatial resolution for land cover classification. Sentinel-1, SAR, and Landsat-8 are preferred for their ability to capture environmental hazards such as coastal erosion and inundation, regardless of weather conditions. Now that we've selected our remote sensing datasets, we now proceed to image processing operations. Image processing operations play a crucial role in extracting meaningful information from raw remote sensing data. These operations include pre-processing, image fusion, land cover classification, change detection, coastal hazard mapping, and integration analysis. Pre-processing involves correcting for radiometric and geometric distortions as well as atmospheric effects to enhance the quality of the imagery. Different sensors may capture data at varying resolutions. Image fusion techniques such as pan sharpening merge multispectral and high-resolution data to create composite images with improved spatial detail. Land cover classification involves segmentation algorithms applied to divide the imagery into homogeneous subjects, followed by supervised or unsupervised classification methods to categorize land cover types based on spectral signatures. Multi-temporal imagery, or imagery taken in different times, is compared to detect changes in land cover and land use over time. Change detection algorithms, such as image differencing or object-based techniques, identify areas undergoing significant transformations. SAR imagery for coastal hazard mapping is processed to detect coastal hazards like shoreline changes and erosion, while multispectral imagery delineates hazard-prone zones based on environmental features. Now, land cover maps are integrated with the hazard maps to identify vulnerable areas. Spatial analysis techniques are then employed to understand spatial patterns and temporal trends, facilitating the prioritization of mitigation and adaptation strategies. Validation is crucial to ensure the accuracy and reliability of the processed data. Ground truth data collected through field surveys or high-resolution imagery is used to validate land cover classification and hazard mapping results. Statistical measures such as error matrices and kappa statistics are employed to assess the accuracy of the classification algorithms. To effectively communicate coastal monitoring data to stakeholders, we utilize GIS platforms like ArcGIS Online or Google Earth Engine to create interactive maps and dashboards that visualize changes and trends. Additionally, we can develop easy-to-understand infographics and executive summaries for policymakers and the public. We can conduct workshops and training sessions for local planners, community leaders, and stakeholders to help them use remote sensing data and tools effectively. Collaborative online platforms facilitate data sharing and discussion among government agencies, NGOs, and local communities. In conclusion, the proposed framework leverages remote sensing technology to address the complex challenges facing coastal areas in the Philippines. By measuring anthropogenic pressures on the coast and environmental hazards, we are able to make better and more informed decisions on our precious coastal resources. Although this project brief is limited to measuring and monitoring, remote sensing can further be combined with modeling and predictive technologies. Through this project brief, I hope to inspire planning units in the Philippines to utilize remote sensing technologies to inform planning and management decisions. Thank you for your attention and see you in my next video.